they're recording.
Oh, good.
So we'll go offline.
Okay. All right. All right.
Do it. Go. Start now.
All right.
Just come and say, introduce yourself.
Okay. All right. Yes. Okay. This is Silicon Valley Fourth Interest Group, and this is our March meeting. And this morning I am Dr. C.H. Ting, and I would guarantee that this is my last talk on the subject. Okay, so be patient with me, and after I get through this talk, I will never present this thing again. Okay, so the topic is severe expansion, and basically it is the equilibrium between gas, liquid, and solid. So here, I finished writing my paper, and last time I submitted to a journal and got rejected. So this time I just threw it on Wiki. Okay. So this paper was uploaded to Wikipedia, and if you just Google Vira expansion and get to Wiki page, and you will find this page. What I'll do is show you this page and scan through this Wiki page and let you see what's in it. And later on, I'll give you a more detailed presentation. Okay, let me get on to. Okay, so this is the paper, Vira expansion. I want to put in Vira equation of state or something, but I don't have the privilege to change the subject. We can turn it off. Let's see.
Are these here?
Just try. All right. Okay, good. Okay, now it makes sense. Okay, so I'll have to, because they already have this category, I can edit anything, put in anything I want, but I cannot change the title of this thing. So, Vira expansion, that's my topic. So I go through some basic thing, ideal gas law, and then this is the most conventional form of Vira equation. Basically, it is not using P function. It's called Z, which is P divided by RT rho, and this expansion rho is the molar density of a liquid. That's one how much molar density. So it's 1 mole of a molecule or substance, and its volume, the volume of it. So this is the basic equation, and then when you write the things out, if you put I think equal sign before and after the title, and it will automatically generate one item on the contents. So this was the topic that I most concerned. Second and third Vira coefficients. These are the second and third coefficient that's in the Vira equation. So basically, it's a B and C. A is always equal to 1, and that's the ideal gas law. Okay, and the B and C states how much this gas deviates from the ideal gas law when the temperature is lowered and when the volume is increasing or density is decreasing. So that's the. So these are the two most important coefficients in the VR equation. But looking through the literature, you can see the consensus for the second VR coefficient is that it is a monotonically increasing function of temperature. So at low temperature, it's very low, and actually it's a negative value. And when the temperature rises, it increases. So this is. Oh, thank you so much. So this is the generally agreed upon the behavior of the second Vera coefficient. The third Vera coefficient, basically it rises, and after the critical point, it decreases. So that's this strange bell-shaped. It's a bell-shaped curve, and I really object to this curve, because when I was evaluating the liquid and gas equilibrium, I found that the third Vera equation has to be a monotonically decreasing function, and it goes pretty much with follows pretty much closely with the second Vera coefficient, but with a minus sign. So this has to increase when the temperature is lowered, just like it has to decrease when the temperature is lowered. This way, the calculation would produce liquid phase at low temperature. If this thing decreases, then that equation doesn't work, and you cannot produce or predict the existence of the liquid phase. So after much study, and finally I decided to do a very detailed investigation on this third Vera coefficient, and try to prove that it is a monotonically decreasing function over temperature. So finally I found some supporting evidences in the literature. Although most of the literature gives you that bell-shaped curve for the third Vera coefficient, but if you really go to the very best Vera equations, the third Vera coefficient behave exactly like what I wanted. So, generally, if you use any equation of state, you can recast the equation of state into the Vera form. For example, this is the most famous Van der Waals equation of state. So it has a very strange term with V minus B in the denominator. But this thing can be expanded around V equal to 0, and so you expand this term into Taylor's equation over V or on the row. Then you can expand it. The Vera equation would look like 1. This is still ideal gas law, and this is the second Vera coefficient. And this second Vera coefficient behaved correctly, because you see if the temperature is lowered, this second Vera coefficient gets smaller and smaller, more negative, and so it increases the temperature is decreasing. So this has the correct behavior. But the third Vera coefficient is a B square, it's a constant, and the fourth is a B cube. So these are basically constants, and that's not correct, because we knew that third Vera coefficient is changing with temperature. It's not a constant. So that proves the van der Waals equation is no good, okay, especially in the low temperature region. So over the years, we have a lot of equation of state, and this equation of state was proposed by B.D. Bridgman. And it is basically a modification of the van der Waals equation. And then this one is can be recast into the Vera form, okay? And so this has the this second Vera coefficient is much more closely much closer to experimental data than van der Waals equation. But then this one also shows some changes, but the changes are very similar to the second Vera coefficient, but it has the wrong sign. Okay, and that's why this B.D. Bridgman equation is good down to the critical temperature, but below the critical temperature it starts to be inaccurate. So over this was let me see in the 1920s, and in the 1970s there are two more much better equation of state, and it almost looked like a Vera equation. So you got the second term, you got the third term, you got remember it doesn't have the fourth and fifth term to jump over to the sixth term. So there's a gap there, and this is very interesting. But what in the difficult part is this exponential term, and it's very it is out of line with a straight Vera equation. So you know, people puzzled over this term a lot, and they just don't know what to do with it. But this equation is much more, much better, much more accurate, and it is very good even to the triple point. So, and then in 1972, starting modify it further, add more terms, but keep the same thing there, but basically have the same form. So these are the most, this one is currently the most accurate equation of state. And so if I try to, you know, expand this exponential term and do a real and find all the components in the third Vera coefficient, and the coefficient, if you plot it with more than 10 hydrocarbon compound, and the second Vera coefficient just behaves like everybody else curve, but the third Vera coefficient behaves like what I wanted. So these two equations give me the correct or the third Vera coefficient that I expected. And I think these equations are much more accurate down to the triple point because they got the correct third Vera coefficient. Okay, so basically I think this proves my point that the third Vera coefficient has to be a monotonically decreasing function, so that the equation of state generate both the gas phase and the liquid phase, and it can explain very satisfactorily the equilibrium, the two-phase equilibrium between gas and gaseous phase and the liquid phase. And the reason is that if you look at this exponential term, and this exponential term is actually a very rapidly converging equation when the rho is when rho is big, okay? So if you take the exponential and expand it in the Taylor series, so the first term is 1 minus gamma rho square. So if you multiply 1 plus gamma rho square with 1 minus gamma rho square, what you will get is 1 minus gamma square rho fourth. Okay, and that means it has one term which contributes to the third Wheeler coefficient, and the next term is the rho to the rho to the sixth, which is one term beyond the rho to 5. So basically you can ignore it, and that. So the reason why these guys, Benedict, Webb, and Robin, add this term is that they want to use third Wheeler coefficient, which can match, the strange bell-shaped curve. But they know this one doesn't work, so they add this term. And this term, in its very strange form, if you just keep the first two terms of the Taylor expansion, and the result is that you have one big term in the third Wheeler equation, which makes the third Wheeler coefficient behave correctly. Okay. So I'm very happy with that. So with a Wheeler equation, well, basically the most best form of Wheeler equation right now we know is you have the first term, which is 1, second term, third term, and then it jumps over to the sixth term. Okay, and if you ignore this, if this term can be ignored, you are with a three-term Wheeler equation. And this Wheeler equation, I think, is a very good representation for all the gases. Okay, so this is the what I call the cubic Wheeler equation, and most substances behave that way. And this equation can be used to accurately predict the behavior of real gas down to its triple point. Okay, and this equation can actually be solved in closed form if you know the volume of liquid and volume of gas at any temperature. Sorry. So these are some details that if you can use some real data to solve for the B and C coefficient. But what I'm most interested, or what the initial purpose of this study is to try to get equation of state which can explain gas, liquid, and solid three-state equilibrium. So here, if we just use the cubic term, only use B and C, we can very accurately predict the PVT isotherms down to the triple point, down to the point where solids start to form. But you see here, the interesting thing about this term is that the B term is negative. So it basically says that it has this term, the first term is the kinetic energy of gases. When the gas molecule at certain temperature, it has kinetic energy, and the kinetic energy keep the molecules in the gas form. Okay, but when the temperature is lowered and when the volume is small, this term starts to get in, and the B term is negative, and it signifies the attraction between two molecules. Okay, and the third term, statistically or according to statistical quantum mechanics, the third term represents the interaction between three molecules, and the three molecules they interact when they have to be very close. And when three molecules are very close together, they tend to repel each other. So you got a C term which is positive and represents the repulsion between molecules.
The C term, you mentioned the quantum mechanical effects.
Yes.
You're talking about fermions then.
No, it's just a regular classical molecules.
Oh, classical molecules.
Yeah, any classical
Because I
molecules.
was going to say with Bose-Einstein condensates.
Yeah.
They can occupy basically the same position.
Yeah. They all repel
If it's
when they're
fermionic, then they tend to repel because when they're getting close
Yeah.
enough, they go, we're the same.
Yeah,
We
yeah.
can't be near each other.
Well, molecules behave that way because they have finite volume and all these things.
Yes.
Okay, so you have a negative term which pulls P down, and you have a positive term which pushes it up, and this is how you get the S-shaped curve, so that the liquid phase can form. So my expectation is that if I put another term there at a very high via term, which again pull the P down and give it another term which pushes up, then I can generate another S-shaped bend at a very low volume, and this will produce the solid state. Okay, so this the N. I don't know what N is. Okay, the exponent. Okay, and generally you would expect that the Lennard-Jones potential, which is 6 and 12, what we call the 6-12 potential. So this term is a V to the 6, and this term is V to the 12. But so I start there. If I use 6 and 12 potential, I don't get that bend. Okay, this bend has to be with a much larger N. Okay, so and this bend has to be very sharp because the volume of liquid and solid is very close, and the volume of liquid and solid when liquid solidifies, the volume change is only about 10%. So this change, pull it down, push it up, has to occur in a very narrow range of V. Okay, and to make it a change in very narrow range, V has to be very large. How big? It has to be above 20. Okay. V has to be bigger than 20. Yeah, 20, it barely produces an S shape. But only to get a decent shape, which closely resemble the gas, liquid, and solid equilibrium, N has to be about 30. Okay, and the bigger the better. But if it is less than 30, the shape, it tends to distort the gas liquid isotherm. So this is what I I was experimenting. Just change the G, change the V, and try to see how this thing behave. And finally, I used the argon gas as the model. But if you use real values for the volume, each different compound has a different set of values. And if you use reduced value, so divide all the volumes with critical volume, divide the pressure with the critical pressure, and they all normalized in the reduced form. And this this set of reduced values are much more general. So most of the well-behaved compound would have this set of value, or very close to them. And so with this reduced form, I can write out the equation of state. And this is the 30th power. And then, it's kind of hard to work with U and W, because U it has the same dimension as a V to the nth power, and W has the same dimension as V to the 2nth power. So if you instead of using this this value, I just use the corresponding volume. So if you use pick a VU and VW and divide it with V and raise that to the nth power and raise that to the 2nth power, it's much easier to work with. So the V, these are just have the same units as the volume. So mathematically, this equation is much easier to manipulate. And then I have I think I have the B and C. I have already derived them from the cubic vector equation at the triple point. Okay, so basically what I'm doing is I try to plot these three terms separately. Okay, I try to evaluate this N and VU and VW. So I just plot these three terms, and this term separately, so I can see how these values changes. So if I have P1 equal to only the cubic equation, and this one is the nth power, and this is 2nth power, and then the total pressure is a sum of these three. And if you can see in this figure, the P1, this curve is from the cubic term, so it has the first three terms. So at the very low temperature, it just grows, increases as the volume is decreasing. Okay, and then the P2, this nth term goes up this way, and this term goes up closer to the at a lower volume. Okay, and if you sum up these three terms, you get this very nice S-shaped band, and this actually corresponds to the solid, liquid, and gas three phases. Okay, and because at the triple point, the critical at the triple point, the pressure, the saturation pressure is very low, close to zero. So you can take zero as P is basically zero at this point. Okay, and then it decreases there, increases, and then I have this nth power, push it up, and 2 nth power pull it down and produce this one. And you have to be very careful with, in selecting. So I selected the, basically I select the VW as the volume of the solid, because that's where this curve pushes everything up. So that's where the solid phase has to be. And VU must be between the solid volume and the liquid volume. Okay? So you can adjust them. So the first thing is to set this one as the volume of solid. And then I raise it to nth power. And then adjust the VU so that I have a nice S-shaped curve. And this S-shaped curve has a, you have to, the area under 0 and the area above 0 has to be equal. Okay, this is called the Gibbs rule. And that's because when the two phases are in equilibrium, and the free energies has to be equal. And the free energy is the integration of this curve. And so the area of this is equal to this area, and these two integration cancels each other, and the free energy, the Gibbs free energy at the solid state and the Gibbs free energy at the liquid state are equal, and that's the condition of equilibrium. Okay? Any question, comments? Okay. So that's to produce this curve, n needs to be 30. And if it is less than 30, and this bend moves over to the right hand, and that would distort the liquid phase. So if n is greater than 30, and this bend is pushed over to the left-hand side, and that makes it much better, much easier to adjust. Okay, so 30 is the n must be 30 or greater. Okay, if it is smaller, doesn't work, because this bend, you cannot produce a bend and pull it down so that it has the equal volume above P equal to 0 and below P equal to 0. And so this is my pride. Okay, this is the equation of state. This is particular for argon gas, but since it is in the reduced form, it probably would apply to most of the well-behaved molecules. And this is the equation of state that produce that curve, and that explain the equilibrium between gas phase, liquid phase, and the solid phase. Okay, so this is the paper. And what I want to show you, let's just go to the slides. Where's my cursor? Here it is. Okay, let me just go through the slides. And basically, I've read everything. But the slide will just make a better summary of what the paper was about. Okay, so it has basically a second, third Wheeler coefficient, and I can cast all the equation of state into Wheeler form for comparison. And cubic Wheeler equation of state is very good for equation of state, the liquid and gas phase equilibrium. And for the gas, liquid, solid equilibrium, I have to add two very high Wheeler terms. Okay. Well, I started this work in 72. with Sam Chen, who was here last time. And when he was a graduate student, I think he just he graduated before he entered into graduate school. So we worked together and wrote a little paper in '72. And I say, well, at the time I picked the van der Waals equation, add a very sharp delta-shaped function to it to to produce another S shape. So that was, but we don't have good computer at the time. We don't have any tools to invest it further until now. So basically, the ideal gas law PV equals to RT. Everybody knows it, but we need to, for a more general representation, we need to use compressibility with the PV slash RT, and PV Z equal to Z equal to 1 for ideal gas. Okay, and then for real gas, you need to add. You have the A, which is always the 1, and you add the B, C, D, E, V, and all the terms. And if you add more terms, you can get more accurate representation of the experimental data. And that's what people did over the years. They just add more and more terms so that they can accurately represent the PVT data over large PVT domain. And if you add more, you get more accurate results. But then people used up to 40 Weyl coefficients, and without understanding the physical meaning of this. So I think these studies are mainly bogus. The only significance is that you have a more mathematical accuracy, but physically you don't have any way to explain these coefficients. So B is the second Weyl coefficient bimolecular attraction, and C is third Weyl equation, which represents the tri-molecule repulsion, and so forth. So that the fourth term is interaction of 4 molecules, and fifth term is interaction of 5, and so forth. But people can have only good quantum mechanical calculation of B, and C, the calculation is bogus because they are based on incorrect data. So the consensus so far was that B behaves this way. It's a monotonically increasing function over temperature, and C has a bell-shaped, and this is incorrect. And what I want to do is prove that the third Weyl coefficient is a monotonically decreasing function over temperature. And so we have historically, van der Waals equation was proposed in 1873. At the time, van der Waals was a PhD candidate. Okay, so you cannot expect a PhD candidate to do much good work. But it's amazing that the equation worked so well that everybody is using it afterwards. And Cameron Owens in 1901 first proposed the Weyl equation. And it's very interesting that he has first term, second term, third term, and he skipped the fourth term. And then he skipped the sixth term and eighth term. But it indicates there's a break there. Okay, so the first 3 terms are much more important than the rest of it. Okay, and then Benedict Webb, Robin EOS 1940, which is good above the liquid state, and then Starling EOS, which is very good down to the solid state. And so these are some of the equation of state, historical equation of state. So all these equations, you can recast them into the vector form, and then you have a much better way to compare the accuracy and the behavior of all these equations of state. And the Benedictive Webb-Robin, and it is this strange exponential term. And this exponential term, its major contribution is to correct the third Wheeler term. Okay, and I think the Benedict Webb-Robin was able to hide its intentions using this very strange term. But if you expand this term, you can see that it makes a big correction on the third Wheeler coefficient, and that's what I wanted. Okay. And then the star, the work of starting the second Wheeler equation, that's the same as everybody else, and the third Wheeler equation, you can see there's no bell shape there. And cubic equation, I think we should bang van der Waals equation in all our thermodynamic textbook from here on, because the cubic Wheeler equation is much more accurate and much easier to manipulate. So we should abandon van der Waals equation and use my cubic Wheeler equation in all the future thermodynamics textbook, I hope. And then this cubic equation can be solved in closed form at the critical temperature, and it has the very nice properties. And it can also solve all the second Wheeler coefficient and third Wheeler coefficient can be solved in closed form if you know the saturation condition. Okay, that's when the gas and liquid coexist, and you have the P saturation, T saturation, and then you have the volume of gas phase and volume of liquid phase. With these data, yes.
Saturation, temperature, pressure?
Yes.
That's nothing like the critical
the critical condition. That's when the gas and the liquid are merged together.
Yes.
So the critical point, the volume of gas and volume of liquid are the same.
Right.
And that's critical point.
Okay,
but below that, the two phase separates.
Oh, okay.
So you have to separate at the saturation condition. You have a gas and a liquid, and they have different volumes. Okay. So if you with these two volumes and the saturation pressure and saturation temperature, you can solve this equation in closed form. So B and C can derive it mathematically without ambiguity. So this is how I solve the equation. But let's don't worry about all these things. So I propose that cubic Wheeler equation should replace the van der Waals equation in all our future discussions. I don't know if people can accept that. But the gas-liquid solid equilibrium, you only have to add these two terms. Okay. So to produce the liquid phase from the gas phase, you need this second Wheeler coefficient to pull the pressure down, and you need the C term to push it up. So you form a S-shaped curve for the liquid state. And similarly, if we use U-term to pull the pressure down and use the W-term to push it back up, and you get a solid phase. So that's all. That's all there. That's all there is to it. And I think this gives you a better, physically a better understanding of the gas, liquid, and solid equilibrium. PV equals to the ideal gas law has a curve like this. Okay.
So what you're saying is E between point E and F.
Yeah, PV.
The ideal gas.
Yeah, P multiply V equals to a constant.
Right.
Yeah, and that gives you a hyperbolic curve this way. Okay, and then if you have the second term, which will pull this curve down, and you have third view coefficient pushes back up. Okay, and that you have the gas and liquid two phases. Okay, and now this one, if you only have the up to the third term using the cubic equation, this will rise up indefinitely. But in the area where liquid and solid coexist, if you produce a sharp S-shaped bend, and this will produce a liquid phase and a solid phase. Okay? So when the temperature is low, when you lower the temperature, this thing goes lower and lower and lower, and eventually they will at the triple point, the pressure is almost zero. So this thing is pushed down, and half of this area is below P equals 0, and half of it is above P equals 0, and there you have the gas phase, liquid phase, and solid phase all at the same time. And let's just don't worry about all these details. So this picture I've already explained it, and then this is that's the Wheeler equation for gas, liquid, solid equilibrium. And I have to remind you that nobody has ever proposed an equation of state which can explain the existence of the solid state, although the solid state is so prevalent in real world.
You got rejected? Your paper got rejected?
Two early versions.
Okay.
Mm-hmm.
What journal?
Journal of Physical Chemistry.
Okay.
Okay, that's the premier journal for chemical physics.
It's much title about physical chemistry.
Yeah, right. Okay. So these are the okay. So the result N and 2N potential, N has to be 30 or above. So that seems to be excessive. Okay. Because we are only at the cubic Wheeler equation, the V only to the first power and the second power, and suddenly you need something N is 30th power. So it seems to be excessive. But as I remind you, quantum mechanically, the first Wheeler term is the kinetic term, and the second term is the bimolecular interaction between two molecules. Third term is the interaction between three molecules, and fourth term will be the interaction between four terms. So, in the liquid phase, an argon atom has 12 nearest neighbors. Okay, three-dimensional picture. And up to 32 next to nearest neighbors. and these molecules tend to interact with each other. So it is not excessive in that point of view. And in solid phase, all the molecules are locked into solid lattice. So the interaction is neighboring atoms are infinite. Yeah.
I think that's where the concept of a phonon comes in.
Oh yeah, yeah.
So you talk about lattice.
Yeah,
It's
yeah.
how they
Yeah, no,
vibrate.
when all the vibration they interact with the whole thing.
The whole thing,
Yeah,
and it's
it becomes waves. Okay.
yes, exactly.
All right.
Yes.
So that's but here, so with 30 n to the 30th power, and in solid phase the n is to the 60th power, and these are reasonable because you need that.
Yes, that's
Yeah.
It sounds like in astronomy, epicycles. Granted, the Greeks were very advanced, but it wasn't a time when they understood the difference between kinematics and dynamics.
All right.
Yeah, that's the thing.
Okay.
Because you could have an infinite number of epicycles, and look, gee, everything matches. Epicycles, yeah,
Okay. Yeah. The thing is that so far we classical mechanics we can solve two-body interactions. We cannot solve three-body interactions. Okay. And the quantum mechanics the same. You have one electron problem, we have solution. But two electron, no solution. Okay. Yeah. And the 3 or 4th and it's 30th, nobody can solve this kind of problem. But statistically, everything's averaged out. So you can.
How does Matter know what to do? I mean, something that small has all the smarts in it, has all these equations and powers behind it and stuff. How does light know how to go at the speed of light?
Yeah. Well,
That's the thing right there. That's a very fundamental question. It's like, is it because of the space that it's in? Because not only is electromagnetic radiation limited to C, but gravitational propagation is C. Okay? And also, here's the other thing. No matter how far apart, here's the question. If you have an excited atom that emits a photon, does it have a destination to go to?
Well, yes, it does, but you don't know. You don't know. You don't know where it's going.
The faster you go to the speed of light in the direction, the closer things appear. So you can say, well, maybe at the speed of light, that the point of emission and the point of absorption are the same. So that kind of implies that not only is there a source, there's got to be a destination for the photon.
Yeah, but although, we don't know what each molecule is doing,
Exactly.
but statistically, if you have, millions of things together, statistically, we can still predict accurately its macro behavior. Okay?
That's like, and it's just because of Heisenberg. Right?
Yeah.
And you all saw him on Breaking Bad. Saw what a rat bastard he was.
Yeah. All right. Okay, let me see if there's anything. The conclusion is that I think the people have the third Vieira coefficient wrong in the literature for all these years. And none of their work are to be trusted. Okay? And a cubic Vieira equation accurately predicts gas-liquid equilibrium. And the people has to start from the cubic equation. you derive B and C accurately. And then, the residue, if anything deviates from this equation, then you can use much higher terms to describe them and maybe explain the behavior. But if you don't have these three terms correct, you need a very huge, very big virial equation to correct the deficiencies of the third virial coefficient. Okay, so when these people are using 40 virial terms, and they can't explain any of them, but it's mathematically correct. Okay, but it's physically unreasonable, and you cannot account for physical behaviors that way. So, and the last, the cubic virial equation can be extended so to create the solid phase. Okay. For every fluid, this cubic has to be solved before considering high virial term. And so, all the literature, you have to re-examine them. And you have to be sure that they got the third virial coefficient correctly before considering anything else.
So what you're saying is
For each fluid.
you just come up with all the different.
Yeah. So generally, if we use reduced equation of state, that would generally apply to all the different molecules. But then each molecule would deviate from it, and so that in the very extensive study of equation of state in the petroleum industry, and they have found that you have a long chain of molecule. They will behave different than if you have a molecule which is kind of round.
Oh,
okay.
Right. Cycling.
Yeah.
Like a benzene.
Yeah. So this virial equation, if you just solve the cubic virial equation, you can just use Excel. Okay.
That's impressive.
Yeah, you can just use Excel to solve it. You don't need any more tools, what they call the multivariable optimization. And when you have a huge number of variables, you can fit any data, right? You just run a computer. Okay. But if you just want to solve the problem in the cubic virial equation, Excel is adequate. Okay. And multivariable optimization is not necessary, and its results are not to be trusted. Okay, so throw away all your thermodynamics textbook and handbook. Everything has to be done right. And for the first time in history, gas-liquid solid equilibrium is quantitatively represented by a virial equation of state, and that's my job. And I think I've finished all the work there, and I don't plan to do any more work, I think. And the result is up in the wiki. You can pull it down and take a detailed look. And I hope that you will enjoy it. And when you read your thermodynamics textbook, make sure you know what you are reading.
So basically, you're the first guy to be able to have an equation of state that's down at the triple point.
Yeah, right.
There you go. There you go.
That's my contribution.
If you need a reference for that journal of physical chemistry, why don't you just get something up on a laser printer and set it right?
Yeah. I think I'll have to write a letter to the editor and informing them of this article.
We have an acronym.
And actually, the government Bureau of Standard, it used to be Bureau of Standard, and now it's It's some organization in the Department of Energy. They have a center, thermodynamics study center in Boulder, Colorado. It's a whole institution devoted to the thermodynamic properties of all the compound. And this organization actually they collect all the data and form a data collection center. And recently they published all the thermodynamic data so everybody can get access to it. And they called it WTT. I forgot it's the so they put all the data, all the tables, all the thermodynamic data on the web, so everybody can have access to it. However, to subscribe to it, you need a yearly fee of $300. If you pay them $300 in a year, you can access most of their released data. I think it's a couple $1,000. Then you can access all the data. If you pay $300, you can access the most the data for most common substances. So I think for last year, I subscribed to it, paid $300 and download all the data. And what I was particularly interested was the second and third Vieira coefficients. And their third Vieira coefficients are not correct, okay? Just like everything in the literature. So I think I need to write them, send them this paper and caution them that they have the wrong data. But I don't think these guys would admit to it or even to consider it. But there is. It's on the wiki. Everybody can read it. I don't have any feedback, probably because the wiki is anonymous. So if you read that article, you don't know who wrote it. Yeah. 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 Well, I'm too old to fight with the journal editors. So any more questions? All right. I think it's lunchtime. Okay. Thank you very much. We'll see you in the afternoon. 1 o'clock, right?
Since we're not live, speed up ahead.
Okay. Okay. 1 o'clock this afternoon. We'll start our afternoon session. Thank you very much.
All right.
See you soon.
Lunch.